All right, we're back, and I'm starting. Okay, so we talked about the reservoirs, the swimming pools from which you can realistically draw particles that escape the planet. The reason that the lower regions in the atmosphere are not that relevant is that there are too many collisions down there. Particles can come from the lower atmosphere and eventually escape, but they change their membership card from troposphere to thermosphere before that happens. And so really the physics that are operating in those regions, thermosphere, ionosphere, exosphere, those are the physics that you want to focus on when you're talking about getting rid of particles. Okay? So the particles that do leave a planet, no matter what, they have to pass through the magnetosphere of the planet. And this is a personal soapbox for me. The term magnetosphere applies not just to planets with dynamo magnetic fields, with intrinsic magnetic fields. Those are intrinsic magnetospheres because the magnetic field from the planet is responsible for deflecting incident solar wind charged particles. Okay? And notice in an intrinsic magnetosphere, of course, the solar wind never really gets anywhere close to the atmosphere. In an induced magnetosphere, like you have at Venus or at Mars with crustal magnetization, the solar wind gets much closer to the atmosphere before it's deflected around. As a matter of fact, some solar wind particles encounter the exosphere or the ionosphere before being deflected around. But the solar wind is still deflected. This is not the moon or an asteroid where the solar wind goes crashing right in. There's something generating currents. Those currents generate magnetic fields that deflect particles around induced magnetospheres like you have at Venus, Mars, or comets. So in both cases, a magnetic field is deflecting particles around. In one case, that magnetic field is supplied from the interior of the planet itself. In another case, that magnetic field is induced in the conducting ionosphere at high altitudes. So that's where you get this picture that you've probably seen about 80 times this week so far, and probably 3,000 times in your career so far as a graduate student, where intrinsic magnetospheres and induced magnetospheres all interact with the space environment, with the solar wind. And in the case of induced magnetospheres, you get something that if you squint your eyes looks comet-like as well. And indeed, comets give induced magnetospheres. So how can particles get out? It's not just genes escape, not just thermal escape. There's a whole flow chart, and I'm not going to go through this. Instead, I'm going to go through the white boxes using only 2 slides for all of them. But I want to give you an idea that particles, as they're escaping from an atmosphere, not just Mars, but Venus and Earth as well, those particles are being given energy, mostly coming from the sun in terms of photons and solar wind particles and magnetic field and solar energetic particles. That maybe photochemistry and diffusion supply the exosphere or the upper thermosphere. And then, I didn't know this before this particle was created, but particles are asked questions as they're about to leave. They're asked whether they're ions or neutrals, and that assigns them a color. They're asked whether they have escape velocity, and depending upon the answer, that sends them some different way. And there are flow charts sort of outlining the physics that could happen to a particle as it leaves. Depending upon who you are, you draw this chart slightly differently, and you end up with slightly different boxes at the top, but we all more or less agree that there are many different kinds of physics that operate and can remove particles. Okay. Blue are neutral processes, red are charged particle processes, so I'm going to do 1 slide each. And I've tried to indicate where I think a process is important at Venus, Earth, and Mars, and the community might not agree with me on the letters that I've assigned, so this is just my own opinion. Genes escape, I think everyone knows. Temperature is a measure of average kinetic energy. In any distribution, you have some particles that are average, some that are below average, but we still love them, and some that are above average. And you can be above average enough that you're above the escape velocity for that particle. Genes escape is important for hydrogen at Mars and deuterium and maybe helium as well, but nothing more massive than that. Some people, and I'm not as familiar with this research line, some people say that genes escape is also important for hydrogen at Earth, even though Earth is much more massive. Of course, genes escape happens with every single species. There's always a distribution, always with a tail. You can always have particles from any mass species that escape thermally. But in terms of being important, it's only important for very low mass particles at Mars, certainly, and maybe Earth as well. Photochemical escape. Here, the energy isn't coming from the temperature of particles in the atmosphere. It's coming from sunlight-driven chemistry. And there are many different photochemical reactions, but here's one example. You have an O2 plus ion. That O2 plus probably came from CO2 at some point in the atmospheres of Venus or Mars. It recombines with an electron, and that recombination produces two fast neutrals. Okay, and at least one of those fast neutrals may have enough velocity, may have enough energy to escape the planet. This is certainly relevant for Mars today. It's also discussed for Venus, and I don't have a lot of information myself on how important this could be for Earth's atmosphere, so I didn't put an E there. Sputtering is another neutral process. This is the equivalent of putting little pebbles into a child's wading pool. Every time you put a little pebble, you throw a pebble into a wading pool, you maybe splash a drop of water out. That's the sputtering process. Collisions from some incident particle splash particles out. Where are the incident particles coming from? Maybe from solar storms, solar energetic particles, but they could also be coming from the planetary atmosphere itself. If you ionize an exospheric neutral, especially at an unmagnetized planet, that ion will start gyrating in the magnetic field, and if it's in the right place, it escapes from the planet. If it's in the wrong place, it goes crashing back into the atmosphere. So the atmosphere itself can be induced to crash back into itself and splash other particles out. Sputtering is a process that we know happens on the surfaces of icy bodies throughout the solar system. It's assumed to be important for the atmospheres of Mars and Venus, but it has never been unambiguously observed. Charged particle processes, I do three categories here. One is ion pickup. In that last cartoon that I showed you, if you take an exospheric neutral and you ionize it in a place where the solar wind convection electric field has access, then you essentially have a V cross B electric field that will accelerate that charged particle away. It will begin to gyrate in that electric field, and this process is called ion pickup. Okay, at Earth, there's a whole suite of processes that I lump together in one term called ion outflow. This is basically any acceleration process that's not a V cross B electric field. It could come from plasma wave heating, quasi-static electric potentials along auroral field lines, so auroral bulk upflow, polar wind, ion conics, all sorts of stuff here. And this outflow term is used in reference to Earth's polar regions for ways of extracting particles from the atmosphere by various electric fields. Finally, bulk plasma escape is a term that I use to refer to all sorts of processes that are related to shear. Okay, magnetic shear, so you could have reconnection in draped field lines around induced magnetospheres, or in the case of Mars, where there are crustal magnetic fields, if you have reconnection. Reconnection is a particle accelerator. Maybe you can accelerate atmosphere away in that way. Also, Kelvin-Helmholtz, a shear-related instability. If the solar wind has access to the ionosphere of a planet, if there's a boundary between the external flowing plasma and the relatively static ionosphere, you can imagine creating shear-related instabilities, waves that steepen and detach coherent portions of the ionosphere all at once, and maybe even things like flux ropes. You've talked, I think, about flux ropes at the sun, flux ropes and expanding CMEs. There can also be ionospheric flux ropes in the atmospheres of Venus or Mars as well. And flux ropes isolate plasma, and there's current in the center. There may be a way to accelerate particles away in that regard. Okay, for charged particles, this was kind of touchy-feely, and it's the way I think about the processes, the way I categorize them as I'm thinking about them, but a really appealing alternate classification scheme comes from Ohm's law. You have all sorts of electric field terms in Ohm's law, okay, and you can associate those electric field terms with a source of energy for charged particles as they're leaving a planet. So this V cross B or U cross B, that's the ion pickup that I talked about. You can have magnetic tension forces, Hall electric fields, electron pressure gradients, and so on. And so when you start looking at it through the prism of Ohm's law, you start to better understand that it's combinations of electric fields that can accelerate charged particles away from a planet. It doesn't just have to be one mechanism. It could be a combination of mechanisms that handshake and each give a particle a little bit of energy. And people in global plasma simulations are now thinking about things in this context, evaluating the importance of each one of these terms in Ohm's law and where they're important in relation to a planet. Okay, this brings us to escape rates and Margie's point from very early on. Based on measurements and also on simulations as well, how many particles are escaping from a planet as a function of time. So there are many different units that could be used. Here, I've chosen the units of particles per second, total, across all species and via all processes. And the escape rates that you see here are all 10 to the 25 particles per second for Venus, Earth, and Mars. Okay, that's roughly what we're looking at based on the observations we have available up to us today. And they're also very uncertain, 2 orders of magnitude, maybe more than that, depending upon who you ask. I've chosen rough numbers here. I don't expect you to read this, but this is a list of the different processes that could be removing particles from the Venus atmosphere, and an estimate of how important that process is for 1 EUV's worth of solar intensity. Okay, and this should drive home the point that there are many different processes that people are trying to evaluate. And all of those processes have uncertainty associated with them. And this is from a paper by Helmut Lammer. I forgot to put the attribution here. All on this slide I did. Bob Strangeway, a scientist at UCLA, has published papers on what's happening in Earth with oxygen outflow. And we'll come back to this concept of it being correlated with Poynting flux. But the ion flux in number per square centimeter per second varies over a few orders of magnitude. And this is for all oxygen acceleration processes happening in the auroral regions of Earth. And for Mars, I know you can't read this at all, but everywhere you see one of these little dots, that's a question mark. Okay? These are escape processes up here. These are species down here. We know something about how much atmosphere is escaping from Mars, but we don't know nearly enough. There's a lot of missing information. Okay, let's put this into a more intuitive set of units for you. First of all, the surface area of all the planets is roughly 10 to the 18 per square centimeter. So if you want to take this global escape rate and start thinking about how many particles are escaping per unit column of atmosphere, you get 10 to the 6 to 10 to the 8 particles escaping per square centimeter per second from planetary atmospheres. Those are much more tractable numbers, I think, than 10 to the 25. Then, if you assume that all of these particles are water, which I have to tell you is wrong, but if you assume that, then that's centimeters of water globally that have been removed over the history of the solar system. Not very much. So if we want, or if we think, it's dangerous to say want as a scientist, if we think that escape to space contributes to changing climate, at least into changing the bulk atmospheric content of a planet, then this probably isn't enough to account for it. That's okay, though, because these are the numbers that we get in the present epoch, and they are woefully incomplete. And we also think that these numbers vary with time. So let's talk about that next. How do escape rates vary? What drives that variation, and how should things have changed over time? Well, there are 2 ways to push on the system, from outside and from inside. So let's talk about outside first, external drivers. Oh, you talk about it first. So thinking about external drivers for atmospheric escape, for how you remove particles from a planet, atmospheric escape rates from terrestrial planets should vary as a function of what? And you have 60 seconds. Ready, set, go. And I'm cold calling on 3 people. 30 seconds left. Five, 4, 3, 2, 1. All right. This group back here. The amount of energy deposited via what? Did you say the amount of energy deposited? UV flux. Okay. Good. Here. Okay, so activity of the parent star, magnetic activity of the parent star. And you guys, yeah. Okay. Okay, what else? Yes, in the back. Maybe. Yep. Temperature of what? Okay. Okay, so now, time out. External. Let's focus on external drivers, things that are not characteristics of the planet itself. Okay. Anything else? Of what? What impactors? Okay. Okay. Yeah. Okay. Anything else? All right. Good. So I'm going to argue externally that really there are three things that can influence atmospheric escape rates. You can expand each one of those three in several ways, but it's photons, particles, and fields. Okay, those are the three things that are interacting with the upper atmospheres of planets and that can get particles moving in various ways. So for each one of these three, I'm going to tell you a little bit about the estimate of the history over the age of the solar system of what photons should be doing for the terrestrial planets. And I'll show you one observation and one model result. So predictions for EUV flux, the wavelengths relevant for the upper portions of an atmosphere. So not total solar luminosity, but just EUV wavelengths that are being absorbed at the top. Here we are today at 4.5 billion years, 4.54 billion years old. And for various wavelengths, as you get younger and younger, the EUV flux should have been higher and higher. So if you think that EUV flux is driving escape, then the escape rates we observe today are low compared to what was happening earlier in solar system history. Yes, that's log. 0.1, 1, 10, 100, 1,000. Yeah. And we go from 0.1 billion years, so 100 million years old, and it's log scaled in that direction as well. Sorry. Okay, there could be many different observations that I report. I'm a Mars guy, so I tend to go there first. And so something that was reported in 2006, which you can't see because I chose too light a font, are ionospheric profiles for Mars during quiet times and during a solar flare. Okay? During an X-ray flare, X-rays are observed at lower altitudes in the Martian ionosphere below the main peak, okay, and increased densities there by a factor of 10. So this is drastically influencing the reservoirs for loss of particles from Mars. Model results, there's an MHD model at the University of Michigan and now at UCLA as well. That MHD model for plasma interaction with Mars and Venus, in this case run for Mars, can be run for all sorts of cases. You can play God. And so case 4 is a solar minimum case, and case 6 is a solar maximum case, and that's the only way in which these two model runs differ from each other, is the EUV flux incident upon the inner boundary of that model, the ionospheric boundary of that model. Okay, and escape rates increase by 2.5 times when you go from solar min to solar max in our current solar cycle. Imagine what might happen if you go to extremely disturbed conditions or earlier in solar system history. Particles. Our knowledge of the history of the solar wind and of particle output from stars, many of you know more about this than I do, I'm sure, but I think maybe we'd all agree that our knowledge of the history of the solar wind is tenuous at best. Okay, it's not really very well constrained. Brian Wood and Jeff Linsky have gone through heroic efforts, and the most recent report, I think, was 2005, and they're still hoping for more Hubble time to constrain this further. But they observe sun-type stars, they observe a hydrogen wall around the sun-type stars and take that as an indication of the extent of the heliosphere around those stars. That tells them something about the mass loss rate from those stars. And so they can take all these observations of stars on these axes that you can't see or read, and they can move it down to these other axes that you can't see or read. But now it's age of the star with this only one number on the axis, 1 billion years. But this is today, this is going back in time. The mass loss rate, the solar wind from those stars should have been higher. What's a mystery is when you get to a really young stars, it seems that the mass loss rate there is much lower. This is constrained by exactly one observation. Okay? But we have observations of Mars and Venus and how much is escaping. Yeah?
I would like to say that psi group, which is the
Yeah.
one there, it's binary.
This is a binary. Yeah. So we're throwing up our hands even more, is what you're saying? Okay, good. That's great, but that doesn't prevent us from forging on, of course. And so here, this is the flux of ions escaping from the atmosphere of Mars measured by an orbiting spacecraft during normal EUV conditions, okay, during high solar wind flux conditions, basically high solar wind pressure, and during co-rotating interaction region events. During more disturbed periods, higher pressure periods, at least qualitatively, it appears that the escape flux from Mars goes up. Okay, so particles make a difference. Oh, and simulations, instead, let's just show a movie from a different MHD model, this time in Japan by Naoki Terada, and released for a press release. That's why it's all fancy. This is basically the density of upper atmospheric particles during normal solar wind conditions, and you can get a sense of escaping particles in this model. And then during disturbed solar wind conditions, the characteristics of the upper atmosphere change, the morphology of escape changes, and escape rates change as well. So observations and models both seem to suggest that solar wind itself has an influence on escape. Fields, this is an old diagram. There might be a better diagram by now, and I have to say that I'm not aware of it, and maybe I should be. But you can estimate what the magnetic field should be, what the IMF should be. At least you can assume that it relates to the surface magnetic field of our sun. And as you go back in time, that surface magnetic field should have been stronger. So you might infer that the IMF, the strength of the IMF, the typical strength, has changed over time and used to be more intense as well. You can look at observations of escape from Venus. Oh, this is Mars, but it looks the same, pretty much the same for Venus. And you can see that there's more escape in the northern hemisphere when you organize by the solar wind convection electric field. The solar wind convection electric field is determined from the orientation of the IMF, the interplanetary magnetic field. So the orientation of the interplanetary magnetic field organizes how escape occurs from a planet This is basically pickup right here, gyrating particles. In models, you could use a hybrid model from Finland, and you can show that the orientation of the solar wind convection electric field also organizes the escape of hydrogen and of oxygen as well, but in different ways. Oxygen is escaping via a pickup process, where finite Larmor radius effects are very important. Hydrogen is escaping via E cross B drift in this model. Yeah. Asymmetry could be due to the crustal magnetic field, so it could be, but not in this representation, because in this representation, everything's been rotated to a coordinate system that's referenced to the orientation of the IMF. So crustal magnetic fields are stronger in the southern hemisphere of Mars, but southern observations are represented both down here and up here in this plot, because everything's been rotated to this common coordinate system. Internal drivers. Okay. Not from the sun, and this is the last box before the very end. How should magnetic field lines, how should magnetic fields influence escape rates? Okay, again, you have 60 seconds. This is your last chance for big discussion, so I want to hear big discussion. Ready, set, go. Thirty seconds. Five, 4, 3, 2, 1. Right in front. What should that do to escape rates? Increase or decrease? All right. All the way in the back, as far from me as possible. Decrease? Why? Something like that? Okay. Let's go to all four corners. Yeah, front. There'll be more what? Okay. Okay, and now you know this is coming because I said four corners, all the way in the back. What do you think? It could even be increase or decrease. If you take Mars and you give it a global magnetic field, will atmospheric escape increase or decrease? Why? Okay. We're all guessing, to be perfectly honest. Yeah. Okay. Yeah. Inclination matters. Yeah, go ahead. Good question. So in 3 words, it's a context-dependent answer. Okay. All right. Let's move on. Okay. Yeah, in my mind, there are 2 main effects. And everything becomes very complicated very quickly, but there are really 2 main effects. Number 1, and this is for Mars, but you could imagine this for Earth's magnetosphere or for Venus as well. I did it for Mars because Mars has crustal fields, and it makes everything look sexy and cool when you do it like this. But magnetic fields are adding magnetic pressure to a situation where there would otherwise not be magnetic pressure. That magnetic pressure, along with the orientation of the magnetic field, can alter the trajectory of incident particles as well. So the solar-wind interaction with a planet is certainly going to change, as we saw in those diagrams before, and that's because there's extra magnetic field strength there. But as you said, and a couple people said as well, adding an internal magnetic field also changes the topology of the situation. And I mean topology in the strictest mathematical sense of the term. Where do the field lines connect? Do they connect at both ends, red field lines? Do they connect at both ends to the planet? Those are closed. Are they open field lines? So they connect at one end to the planet, blue, and at the other end to the solar wind. And for this simulation of Mars, it's a completely naive superposition simulation. So the locations of the open field lines, I believe, and they've been validated by observations, how the field lines drape, I don't believe that at all. Or is there an unconnected topology? Are the field lines connected at both ends out to the solar wind and at neither end to the planet itself? Those are the green ones. So these 2 effects, I think, are what influence the motions of charged particles near the planet, prevent some things from happening, enable other things from happening, and therefore influence how escape proceeds. So this, I think, is the most boring slide of the entire time because I didn't have any room for pictures. But I went through each one of the escape processes and tried to just think qualitatively about what the addition of a planetary magnetic field would do to that process. On the left, you see the neutral processes. Genes escape. That's driven primarily by solar EUV photon flux. The energy deposited by the solar wind is very small in comparison to EUV. Magnetic fields should have little or no influence on escaping neutrals unless they're throwing a bunch of ions in the way of the escaping neutrals somehow. So there should be almost no influence of magnetic fields on genes escape. The other 2 neutral loss processes, though, both involve ions at some point in the process. Therefore, the presence or absence of magnetic fields should make some kind of a difference. Whether it's important or not is debatable or to be investigated. So for photochemical escape, we started with an ion, O2+. That ion might have been created, probably was created at low altitudes by photoionization, but you can also create ions by electron impact or charge exchange. That might be reduced when you're shielding the solar wind from the top parts of an atmosphere. And B fields affect the motions of ions. So if you're not really in a collisional regime, this O2+ could be traveling large distances, and its trajectory is influenced by magnetic fields. So there may be an indirect effect here. Sputtering, I said, is caused by atmospheric ions gyrating back into the planet and crashing there. So if you add a magnetic field, you change how sputtering works, you change whether sputtering can happen at all. I think that there should be a large reduction in sputtering when you add a magnetic field to a planet. Again, we've never observed sputtering happening in the atmospheres of Venus or Mars unambiguously. Pickup, the solar wind electric field carries away atmospheric ions. If you're on closed field lines when this happens, as you have already mentioned, you don't get carried away at all. You get carried back and forth along those field lines, or if your pitch angle is right, then you crash back into the atmosphere. The presence of magnetic fields should reduce pickup escape. Ion outflow is a whole bunch of processes that I swept under one common rug. But the cold atmospheric ions are accelerated away by electric fields. And magnetic fields should influence the motion of ions. It's not clear to me in which direction this should go. And finally, bulk escape, the shear-related processes, reconnection, Kelvin-Helmholtz, flux ropes, most of these require that the solar wind and ionosphere lie in close proximity to each other. This doesn't happen at Earth. The solar wind never gets anywhere close to the ionosphere. So bulk escape should be most effective when you do not have a planetary magnetic field. Okay, here's the big question, the question that we're pretty much going to end with. So the magnetic fields shield atmospheres. And this is something that many people, including myself until the last couple of years, assumed had an obvious answer. I assumed that the answer was yes, magnetic fields do shield atmospheres. They're keeping the solar wind away from a planet. The solar wind can get close to Mars and Venus. It can strip atmospheric particles away. But this is a question whose answer has been re-examined recently, thanks mostly to Bob Strangeway at UCLA, and I think he's on a great track right here. I think this is something that the community needs to be thinking about. And especially the exoplanet community assumes that magnetic fields inhibit or reduce atmospheric escape. That is not necessarily true. Okay. And we have data in our own solar system that can help us to answer this question. So here are the arguments for a shielding influence. And you've read this by now. But I'm going to read it to you again, and that's what you get for reading ahead while I was talking. The magnetic field strength prevents direct access of the solar wind to the atmosphere. We've shown that ions are involved in 5 of the 6 loss processes. So the presence of a magnetic field should influence how atmospheric escape works, certainly. And maybe you got a sense, and I certainly have the sense, that there should maybe be a net reduction in atmospheric escape when you think about many of those processes. And there's empirical evidence from the present day planets. Mars used to be warm enough to support liquid surface water. To do that, you need probably a bar, maybe 2 bars or 3 bars of atmosphere on that planet to get temperatures above freezing. Okay, that atmosphere had to have gone someplace. Venus lacks water, which was probably lost to space, and the isotope ratio suggests that stripping to space has been important. It hasn't all gone down. At least some of it has gone away to space in meaningful ways. Okay? Also, there is this paper that was alluded to before, and I have to tell you, I don't really buy the results of this paper, and you can't see it anyway, so you'll just have to trust me, that looked at a CME, passing by Earth and Mars when they were on the same Parker spiral field line. And it took the escape rate, which is in orange that you can't see, and from Earth as a function of time during this event, compared to a normal escape rate during a quiet period at Earth, which is in black that you can't see, and got maybe a 10% increase in escape rates. During the same event as it passed by Mars, which is only sampled during certain portions of the orbit of the Mars Express spacecraft, escape rates went way up as the CME passed by. And this suggested to these authors that Mars and Earth respond differently to the same event, and that escape from Mars is much more intense during these events. What isn't shown in this plot are the next 3 or 4 orbits, and at least one of them has escape that is sort of 80% of this, long after the CME should have passed. So I'm not sure I buy the results of this paper. But this is one line of argument, and I think I'm mostly in this camp right now still, even though I think we need to re-examine this question. Yeah? Correct. Yeah. CMEs evolve with different distance, and even if it didn't evolve with distance, Mars may have encountered a different part of the same CME. Yeah. Okay, why not? Why might not? Magnetic fields might not matter. Why not? Well, number one, the measured loss rates are all comparable. I kind of discount that because they're all uncertain to 2 orders of magnitude. So they could be very different, and we just don't have basically the ability in the observations we have to discriminate between differences. But certainly the differences are less than a couple of orders of magnitude. But here's what I really like about this idea, because it's just physics. Magnetic fields are big energy and momentum collectors. Okay? They make the planet have a larger cross-section to the solar wind than it would have in the absence of a magnetic field. So if the magnetic field can harness that energy and transport it down field lines to the ionosphere, then you have a lot more energy encountering the atmosphere of a magnetized planet than you might have otherwise. It's just all focused in a very narrow region, in the polar caps. And this can change how the escape works. It can change the species that are being pulled out of the atmosphere so that heavier ions are favored because you're getting more energy in one place. More energy will mean that heavier ions can escape more easily. There are several caveats, and I had a really great conversation with Bob Strangeway last week, and I think we're both on the same page here. There are large error bars on the escape rates. Just because a magnetosphere collects energy from the solar wind doesn't mean all that energy needs to go into escape. It can go other places too. Also, not all escape that's being measured from Earth actually leaves the system. Much of it goes into the magnetosphere, and it's an open question right now in that community. How much returns? I asked Bob Strangeway what the value is, what fraction of this observation actually escapes the system, and he said 50% plus or minus 50%. Depends upon who in the community you ask. Okay. But this is a really cool question, one to be examined. All right, just 3 slides of prospects, 1 minute each. Where are these kinds of investigations headed? What's needed? What do I think is really cool to be working on in this community specifically? Well, one big frontier are models. And we heard in the last talk about integrated models from the ground all the way to space. They have these models for Earth, and these models are now being developed for Mars with their first results have come out in the past year or 2 as well. But let's just focus on global plasma models alone. Those models tend to be developed for one planet and one planet alone. And this is the right way to develop models, to focus on an object and make sure you have it right. But if we're going to be doing synthesis and comparison between bodies, you'd love to have a model that has a dynamo knob that you can turn on and off. And I say this naively and glibly because it's really hard to have that knob. When you turn the dynamo knob on, you increase the magnetic field strength, and if you have a kinetic model, suddenly you've completely changed the spatial and time resolution that's required to resolve things appropriately and to capture the right physics. But that hasn't stopped people from starting to try with really weak fields in hybrid models. I also think hybrid models are important if you're going to be doing outflow type processes in polar caps. I think MHD isn't the right tool there. It's a great tool, but not the right tool there. So some people are starting to move towards model development where on the same platform you can move a knob and change between relevant systems. And maybe in the next few years we'll start to see dynamos added in appropriately. Fran. I agree. So the question was, not only is the dynamo knob important, but the boundary condition, the inner boundary condition, that's also critically important as well. I completely agree with that statement. I think Venus and Mars, it's easier to get a model to work for both of those objects. You're changing some density profiles in the upper atmosphere. You're changing some of the species, but it might not be all that hard to go back and forth between those 2 objects. I think the boundary conditions when you go between unmagnetized planets and a global magnetosphere, that's another really hairy problem. And I mean, I can't say much more than that other than it sounds hard, and I hope someone else does it. Yeah. Another frontier, MAVEN, you heard about that in the last talk, so I'm a co-investigator on the MAVEN mission. It's on its way to Mars right now. It will orbit the planet and study almost everything that I just spoke to you about for the last hour and a half. I could go on at length about the mission, but instead I'll just tell you what the acronym stands for. M stands for Mars, A stands for atmosphere, and V stands for volatile, any species that likes to exist as gas in an atmosphere. E stands for evolution. And this is what happens when you let the scientists pick their own acronym for the mission, and it means wise one. And we have almost any instrument that you could imagine wanting to have to study atmospheric escape processes from a planet. What's really cool about MAVEN is it's taking many observations that have been made on previous spacecraft and adding some observations that have never been made at Mars before and putting them all together so that we can look at the sun and we can study all of the relevant drivers coming from the sun: photons, particles, fields, solar energetic particles. So we know how all the knobs on the system are going to be set. We're going to study the reservoirs, the swimming pools for particles, thermosphere, ionosphere, exosphere. We're going to understand the state and spatial and time variability of those reservoirs. And we also have instruments that will measure the escape. For ions, the orbit of the spacecraft will paint out a big butterfly net behind the planet, and we can count how many ions. That's my job. I just count. That's my whole job on the mission, is to count how many ions are leaving the planet. We use ultraviolet observations to infer the neutral escape as well. So this is a whole mission designed to study heliophysical interactions with an atmosphere. It's not just a Mars mission. I think it'll tell us about how atmospheres everywhere work. And so that takes us to the last frontier, which are exoplanets. And I've kind of covered this already. We now know of many exoplanets, thousands of exoplanets, and you can extrapolate from that, and people have, to say that there's somewhere between 40 billion and 100 billion planets that could have been habitable in our galaxy alone. In 1995, we knew about 0. So we've gone from 0 to tens of billions in 20 years. So which one are you going to pick to investigate first? Hard to do. Yeah. I mean, I don't know, but you're going to use every lever you have at your disposal. You're going to use distance of the planet from the star, solar intensity, luminosity. You're also going to use magnetic activity of the star, whether or not you think the planet has a magnetic field, whether or not you think atmospheric escape is important. And right now, it's the Wild West in this area. There's a lot of room for good, solid work. There are a lot of models being developed that are good models, but are relatively unconstrained in what's put into those models. And what I think really needs to happen are that the observations and knowledge that we've gained from our own solar system objects need to be used to more tightly constrain how we're thinking about exoplanets. So I think that's a big deal. Okay, so we're at the end of our time now. So instead of having a discussion, I'm going to leave this up for you to think about and for you to discuss on your own. Hopefully we've covered most of what's here in my talk, except for M-type stars, M-class stars, which I'm hoping were discussed earlier in the summer school here. All of these things have relevance on whether a planet's climate is changing, what the climate might be like, and what its surface habitability might be like as well. And I'll say right now that there's no right answer to this question, at least with our current state of understanding. So, all right, thanks a lot.